Beautiful. Thank you. Ciao Lugano. That's how much Italian I know. Sorry for that. um, so in the next 40 minutes or so, I'm gonna talk about eBPF. Oh, yes. Sorry, I wasn't presenting. We're gonna talk about eBPF and what does it mean, why it's gaining a lot of hype that is gaining lately, and see some of the tools that we can use and how basically we can embrace it in whatever use case you have for it. Anyone here probably not using but heard about eBPF before? Cool. Is anyone using it? Cool. And probably are using it but not aware of it yet. Why this presentation? So few months back, I was, while commuting, listening to podcasts. A podcast about everything that's I listen to podcasts while commuting, and one of the episodes was around DevOps, and they brought Liz Rice, which is a known face in the eBPF and DevOps community, and she talked about eBPF, what it is, and what it offers, so on and so forth. And then the host made a very tricky remark, or intelligent one, and he said that eBPF is one of these technologies that everyone is talking about, but nobody really understands, similar to LLMs and all the hype around them today. So that's why I decided to have a look. And while having a look, I said, why not doing a presentation about it? And luckily it got accepted. So basically, this is me sharing the learning that I collected throughout this journey. So basically, the history of eBPF. It originates from BPF, Berkeley Packet Filtering, and it's basically a way to filter network traffic or packets. It looked like this. It's similar, very similar to assembly. It was very hard to write, very boring, no high-level language it supports, and basically you're typing assembly code, and that is, I think it's ARP packet, and it says if basically the header of the packet is equal to the ARP packet, not equal, execute the drop, which is on line 4, which will return 0, meaning drop the request. If we return any other results, line 3, it continue its journey to the user space. It was within the kernel. It was super powerful and enabled the developers to do packet filtering, but nothing more. And then, so the paper were wrote in 93, got introduced in the kernel after 4 years in 97, and then it stayed there until CComp was merged in 2012. And CComp is basically a way to limit the privileges given to a Linux process. And why I mentioned you probably using eBPF without knowing it is because CComp is part of the Docker profile. So basically, Docker and containers use CComp extensively to limit the privileges that you can give to a process. Docker is a bad example because it basically allows most of the things. But if you're a DevOps guy or more into the Linux systems and being a sysadmin, you want to tweak how many privileges you give to your processes, and basically you would work with CComp extensively. And then the CComp was the next big step into the BPF world. And then a lot of discussion has been happening, why not taking that model that we experimented with in BPF and allowing more interaction with the kernel. And the idea was to, similar to a plugin model, have a plugin that can interact with the kernel, of course in a safe way, in a fast way, but enabling us basically to load plugins to the Linux kernel in order to execute some code. And that's what we saw in 2014, was very limited, but then slowly we started introducing more and more features, and that's what we are going to cover in this presentation. So the question is, what is the relation between BPF and eBPF? Basically nothing. eBPF has grown so much that what was intended in the original paper, known as BPF. And you may be asking, because eBPF mean basically extended Berkeley packet filtering, but there is no relation whatsoever between what BPF was and what eBPF has become. And naming it is hard. We are developers. We know that naming sucks. So that could be a var or something, but luckily eBPF is something that is hard to pronounce, but it has a meaning. So we're stuck with eBPF, and that's what it's known for the industry. Now in 2024, BPF and eBPF pretty much mean the same thing. In the Linux community and sysadmin guys, they use BPF more than eBPF. In other conferences, they are more using eBPF because that's what it is. But if you heard BPF and eBPF, know that this is what presentation is going to cover, so it's used interchangeably. So why? Why do we need a way to extend the kernel functionality? The first thing is understanding what the Linux kernel does, and for that I have a, probably if you see, execute a small demo would enable us to do so. So everything in Linux kernel is a file, right? So everything in Linux kernel is either writing in a file or reading from a file, so it's a file system based. So anything we execute, such typical command, C, I believe, and then PS. PS basically lists all the processes that we have running, right? And then for this simple command that we execute probably dozens of times a day, probably hundreds, if you are dealing with containers and stuff, or processes in general, there are a lot of things happening behind the scenes, a lot of interaction between the user space and the Linux kernel. And for example, the open add command, which tries to open something, probably I need to make it a little bit bigger, got executed a little bit 600 times. Because it's fast, we don't notice it, but there's a lot of interaction happening between the little program that you execute in the user space and the Linux kernel. So that's basically it. The Linux kernel is the brain that empowers everything that you run in the user space. And the more closer you are to the kernel, the faster your program will run, because there are privilege limitation and a lot of safety guarantees that the user space and all the rings in the what's called software in the OS operating system runs in order to guarantee that everything we send to the kernel is actually safe. And the same thing applies for all the Linux commands that you execute pretty much daily. They all have a lot of interaction with the kernel in order to perform this functionality. So in all the programs we're on, in the higher level languages that we have, we're running in the user space. Be it Java, Rust, Go, whatever your programming language is. I hope it's not JavaScript, but anyway, it runs within the user space. And the kernel, what it does, it basically ensures that the interaction with the file system is there. So your program interacts with the high-level language. Your high-level language set a command to using the execv to the kernel, and the kernel dispatch it. So it gets your resources from memory, it stores your data structure in memory, it runs these processes, and it does all of that we can see here. So the interaction between the user space and the kernel pass through what we call a system call interface, and then it does file management, memory management, process management, and all of that. And the kernel interacts with the hardware, and it's the layer that guarantees whatever we are trying to run. And if we want to extend the kernel functionality for whatever reason, either security, networking, or something that you want to improve for a use case that you have, pretty much we had two use cases. Either building it directly in the Linux kernel. And by building it, you would need to make a proposal to the Linux community, and Linus Torvald would need to read your proposal, approves it, because like it's a pretty, not a democratic model in such a way. So Linus Torvald will have a say in your proposal, and imagine you managed to convince Linus Torvald and the whole Linux community, you made whatever necessary changes you have, and it got merged. Party, right? Well, not really, because like if your change is merged in a Linux kernel, it needs a couple of years until it land into whatever Linux distribution you are using. So there is what, 4 years of wait before you start using whatever functionality you have. So there is a whole amount of investment, and it is not guaranteed, given that more than 50% of the proposals gets dropped from the Linux kernel. The other option is actually to build a kernel module. And kernel module is a specific module that you add within the Linux kernel, and you are using basically unsafe APIs. APIs that are not safe, that are meant to be used exclusively by the kernel functionalities. And that means that you are going to be on your own, meaning that whatever changes are made to the Linux kernel will break your module, and you would need to maintain it for whatever years to come. So both options are available, but are not optimal. And that was the idea behind eBPF. So eBPF is basically a way to extend the kernel, allowing us to add functionality, of course, making it user-defined because we want to interact more regularly with the kernel, making it sandboxed, meaning that we want to ensure safety and guarantee that whatever runs in the kernel is safe, and it needs to be executed by the kernel. Why we care about safety? Because it's the kernel, and if the kernel crash, meaning that everyone will notice, users, your manager, your boss, and you will have a hard day. So yeah, that's basically what I meant. It's a way to make the Linux kernel extendable at native execution speed. And it is important because the code that we deploy and run in eBPF is basically a kernel code that gets deployed into bytecode and able to run at similar kernel code as it was written for the kernel from day one. How it does that? So you have a high programming language, and we will see what other languages that we can use. But know that you will have, or your code will be either mapped to C or C++ or Rust, because those are the two programming languages that are supported within the kernel. For the user space, you can use whatever language you are happy with. So you write your code in C, C++, or other languages. It got compiled into a bytecode, similar to what we have in Java if you are a Java developer. That bytecode is a temporary state that ensures compatibility, interoperability, and a lot of things. And we compile that bytecode, and then we load it into the kernel. And that's what eBPF tooling enables us to do. So before loading it into the kernel, it needs to pass what we call the verifier. So the verifier is basically a set of rules making sure that your code is safe to run within the kernel. What it means that you don't have an endless loop. So for while true and run it, that won't pass the verifier, because it makes sure that whatever execution path you have, it will reach a stable end. It guarantees that you are not accessing any memory that you are not allowed to access. So it has a lot of rules in order to make sure that the bytecode you are loading is actually safe to run. And if you ever try to build eBPF programs, you will scratch your head with the verifier, because that's the hardest part within the eBPF tooling, and it's for legitimate reason making sure that the program is actually safe to run. It was really hard to work with in the beginning because the debugging messages were meaningless. But the community has put a lot of effort in order to make why the verifier was failing more readable. And then once it passes the verifier, the next step is the JIT compilation, or just-in-time compilation. So we compile the bytecode into native code, and that's what enables us to have a native execution speed. So the code that we have is pretty much as it was written for the kernel since day one. A quick example here is this one. As any conference session, we need to have a hello world application. Yeah. Say it again. maybe with the demo you will. Yeah. So in eBPF we have two levels. We have the user space code that if you need to read and write, and we have the kernel space, or the code that's meant to the kernel. So the first part is, this is the kernel space, and it's a C. So I'm using BCC, which is a Python library that basically take the C code, compile it into binary and whatever. And basically, I'm printing here a simple message saying, hey Logano, I'm an eBPF program. And then I'm loading that program. This is a utility from BCC library describing my program, saying what system calls needs to be assigned to that. Because like, if you mentioned at the beginning, there are system calls, and there on those system calls, there are a lot of types, processes, memories, whatever. So we are attaching a system call to your program. And then you are, so here is kernel probe. It's a type of eBPF program. We'll get into that in a minute. And then we're assigning both, and then we're running basically print trace. Pretty simple. It's basically load this eBPF program into my code and run it. Back to your question, if we run strace.eBPF Python 3 and hello.py. So strace is basically intercepting the execution. I'm filtering BPF programs and running it by Python. This is what I explained in the beginning. So we are so this is my program, and you can see that it was first compiled and then loaded to my program, and I should have a hello something here. Oh, this is a little bit big for me. Hello, maybe, if you will. No, here. Yeah. And behind the scenes, what happens, there are a lot of things that basically ensure that the program is safe to run. So each program have an identifier. So here are a lot of metadata about why the program is running. So it's the program type is key probe, a number of instructions to make sure that all the instructions there is 20. The license is GPL, since Linux is GPL, so anything in there needs to be GPL compatible for license. And a lot of information, like the number of functions, where to call, how much the program is for footprint scenarios. So there are a lot of metadata that happens behind the scenes that make sure that what we execute, it's actually what we loaded. So yeah, did it answer your question? Cool. So that's basically it, and it runs continuously. That was a quick one, eBPF runtime. The verifier, yeah. No, that's a VM, sorry. I should have mentioned that. I'm using a very lightweight tool called Lima, Lima virtual machine. So I'm having here basically an Arc virtual machine running. So behind the scenes is it's a virtual machine running Linux. Nothing in this presentation is run on Mac. The runtime, why it's nice to have eBPF compared to other things. It comes with security and safety in mind. So the verifier will ensure that your code is safe to run, and it provides us with this sandboxed environment, making sure that the program is actually safe to run. It provides what we call continuous delivery, with something that we never were familiar with in the kernel programming. For example, if I change this to, I was about to type Italy because, yeah, whatever. What should I put? Java, for sure. Here you go. You got it. And then if we run it again, hopefully. Hello? Yeah. So that is something that would have taken a lot of time and a lot of testing before it reached the kernel. And that's continuous delivery aspect is really cool when it comes to eBPF. And that's why there's a lot of tools that are built on top of eBPF, because it allows this continuous delivery way of thinking that is needed in this new era of, or more cloud native environment. It's efficient. It's like we have this kind of temporarily uh, bytecode program that we can load, and between the loading of the program, we ensure that basically the program is safe to run. And this byte compilation can enable us to basically run multiple languages as long as it runs or provides the bytecode at the end. And then it's standard. Standard is important here because if you remember the module example, we said that the APIs are not safe. eBPF APIs are safe. So with each kernel version, we introduce new APIs, and that's meant to be public APIs, meaning that they put a lot of effort into standardizing them and supporting them for more years to come. It's with safe, I mean, the verifier will ensure that your program is, it's kind of, you can think of it as kind of integration testing. It loads the program, it runs it, it makes sure it executes a lot of options, it verifies the memory, the processes, and everything that you run.
But when it runs, it doesn't run in a special sandbox.
No, it's in the kernel.
Okay,
Yeah.
okay.
I don't think having a sandboxed environment in the kernel, it's safe because like it's the kernel, and then you would have another piece of software running side by the kernel, which is similar to the user space. What we want is something to run directly in the kernel. But sandboxing is ensured by the verifier, which is like there's a kind of a environment that it makes sure that your program is safe to run before it lands there. Hooks. eBPF is an event-driven kind of architecture or a program. Hooks or attachment points, or we can call them attachment points as well, is what are you interested in to run your program in the Linux kernel. Qprobs and uprobs. Qprobs are kernel probes, and uprobs are user space probes. So we can attach both of these. XDP are more for networking, and we will have a demo for a load balancer, basically express data path. So load balancing and stuff, reading the headers of network and such, that is one of big use cases that eBPF is used for. C groups, mainly the BPF part, the processes, the rights that they have, and so on, and then everything that comes with networking is one of the things. So there are a lot of attachment points that you can attach your program to, but each program will have a set of attachment points. So you don't run your program without knowing which attachment points you would need to run your program into. Because like what happens is, in the execution path, you basically have an event, listening to an event, or the kernel does it for you, listening to an event. Let's say, for example, in our demo, we did qprobs, and then the kernel intercepts the request that is coming, and then if there is someone that is listening, it's basically redirected to you to do the handling and provide with a response, either drop or continue or something like that. So it's kind of a similar event-driven approach where there's listeners to whatever request is happening, and you do your logic and you return the results to the kernel to continue the handling or dropping it. Where we can have attachment points, pretty much everywhere. Listening to storage, file systems, network, memory, system calls, whatever ongoing between the users or processes, memory, whatever. So since you have access to the kernel, you can listen or interrupt everything, which is really powerful. It enables a lot of scenarios from a security point of view and also networking point of view. eBPF maps. I mentioned in the beginning that there is a kernel part and there is a user space part. We didn't see much of the user space part yet, but there are. And eBPF maps is basically a data structure where we can save our data. To do any kind of program, you would need to save your data somewhere, and eBPF maps is a way to do so. It's basically a simple data structure, either arrays, hash maps. They are basically hash maps, but they got tweaked to adapt to a lot of scenarios, arrays, lists, and so on and so forth. And the scenarios that they can be run to are basically different. So you can, with the continuous delivery part, you can load your eBPF program, you can start it, save the configuration into eBPF maps. Whenever you want to restart or introduce a new version of eBPF maps, that configuration is there, so your programs use it and start again. You can share data between the user space and the kernel in different ways. For example, in login, what we do is we read the data from the kernel, put it into eBPF maps, and then the user space does the processing of that, either sending it to an data processing tool or something, but that's way of sharing data between the kernel and the user space. You can share the data between the user space and the kernel in the other way around, meaning that you have some configuration, you want to have it on runtime, in real time. You can configure it in your user space program and then inject it into the eBPF maps, and your eBPF program will read it, basically. There are different types. As I mentioned, hash tables were the first ones to get introduced, and then they were tweaked basically to serve different needs. Arrays, least recently used maps, queues, stacks, different type of data structures that can be used for different things. Time is running very fast. I have a small demo about eBPF maps that are probably going to skip, but it's you'll probably get the idea. So same as the first one in basically this part. So we're loading the program in this, whatever. Here, I'm declaring a map, which is a hash map, that is have a syscall as a key. And then I'm interested in the exec v, which is number 95 or 59. So whenever I get an exec v, which its key is 59, I'm incrementing the counter, and then updating the hash map, and then continuing the execution. And then additional code here from the user space. So that's a kernel I update by the user kernel, or by the kernel, user kernel, by the kernel, and then read it from the user space, basically. Hopefully, if I'm lucky, it should run. Python 3, hello, map. Yeah, so I have one, and if I go here and execute ls, it should update it, execute something else like ps. Whenever there is something happening, it goes there and execute it. Basically, you can, yeah, just to show that you can read it from the kernel and get it from the user space. An example that we can, to show the importance of the verifier, is if we remove this one. In any programming language, if you don't check for the P, if it exists, it will run fine by the compiler, right? What would happen if we run this one? Permission denied. Let's just pro. Yeah, map value or null. So that's a message from the verifier. It says that the map can be null, or the pointer value can be 0. Is that what it was? Or the map could be not initialized yet, and then that could be an issue in the way you look up in the map. So it makes sure that the program is actually safe to run from an algorithmic level. Helpers, to interact with the kernels, we need to put a lot of code. And eBPF folks, what they did is they exposed this as utility libraries that you can think about. Like, for example, to get a random number, you would need to call a helper library. To get the C group ID or container group ID, you would need to call a kernel library. So basically, think about it as a lot of utility functions that are available for you, stable, that you can use into your eBPF program, and those are interact directly with the kernel, which allow for more enjoyable developer experience. Functions, it was introduced a couple of years back. Funny enough, in eBPF, up until recently, you had to write all your programs in a single file um, without functions. You can't reuse your functions. Or if you did, you had the always inline, which is a trick to the compiler, which basically collapse everything in the end. Now it's, yeah, they got the idea that functions are necessary, especially if you are building big projects. So functions has been added as any other programming language you would use. Tail calls are similar to functions, but it's a way to decompose your program into reusable blocks. But are different to functions because function, when the execution end of a function, it runs back to the main process. In tail calls, basically the program is just moving forward. And you can think of it as a couple of microservices where the call is just going upward and not going back. So you decompose your program in its specific blocks, and the execution of your block make the final project or final application that you are building. Use cases. What we can use eBPF for. Networking optimizations. There are a lot of projects that has been built with networking in mind using eBPF. I'll come to a more concrete example in the end, but since you have access to all the layers of the networking stack, from the socket from the network driver, you can offload even the program into a network device. So the request can be treated within the network card before even reaching the kernel, which is super powerful if the device or the network card supports offloading programs, which is a nice feature of eBPF. You can have traffic control programs, IP or TCP programs in there, and then all the way up to layer 7 within the application. And that is one of the big use cases that eBPF is used for. Tracing and profiling. Brandon Gregg, one of the first contributors and maintainers of BPF and eBPF, wrote a set of tools basically that enable interaction with eBPF. He basically wrote all what we know as Linux commands with eBPF, but even beyond that, to interact with all the layers and all the components of a Linux system. Command line based, very cool, very powerful, and give insights over what's happening. He started using the tools when he was with Netflix. He was a sysadmin there, part of the reliability engineering team at Netflix. And Netflix were using eBPF way ahead of, like before it became what it is today. He was even using it as part of, it was in beta mode even. So it's really great set of tools in there if you wanted to give it a try. Observability and monitoring, that's one of the big use cases that are a lot of tools within the cloud native community are building it. Since within the kernel you have access to everything, it enables you basically to take the data from the kernel, dump it, and then load it into your monitoring tool. Especially in cloud native environment where you have a lot of containers, the kernel is shared between all your containers. So instead of having monitoring per container, you have it once in the kernel, save space, save performance, and also save the overhead. Security, you have basically you can monitor and tweak everything, both from a network level, process level, memory level. You can write eBPF program that basically detect unusual behavior and limit access to some scenarios. If you want to start, or what you can use to build eBPF programs, C and C++, mentioned those in the beginning. eBPF is part of the eBPF initiatives in C++. BCC, very easy to start with if you're a beginner like me. It's a Python that you can use, and it's part of the iVisor and within the work that Brandon Gregg was doing. If you are happy with Go, there are two projects, eBPF Go, part of the eBPF project as well, and then Cilium have their eBPF Go that they are using to build their tools as well. If you're a Rust guru, a lot of people talking about Rust right now. Aya is a very cool one. I did my second demo with Aya, but libbpf is also RS is a supported library in there. And then Java. When I did this talk at DevOps, this slide wasn't there. So it's a new one. And then with a friend, we are starting kind of a cool project. It's similar to BCC with Java. So it's basically this one. So we're just starting. We're just supporting the few examples that I shared here, but they are in Java. But if you want to give it a go, start playing with Java and eBPF. It's there. We just wanted to offer an option, and it's very similar to the Python code that you have. We are building it with Panama in mind, or with Panama features, which is really cool. It's open for contribution if you want, so contributions are welcome. It works on my machine. That is one of the things that eBPF suffers from as well. You asked about the temporary state, and that was because, so when we have the bytecode, we have what we call Linux, the headers in Linux. And those Linux are specific to your architecture type and Linux kernel versions. Some functionalities or some headers would be available in some version, but not in the others. And when you load them to the kernel, it means basically that you will get some issues because a header or a pointer is not there in next version of Linux OS. The community introduced BTF, which is like BPF type format, if I'm not mistaken, and it's basically standardized that way and add another layer, which is the BTF. And the role of that BTF is basically ensuring the mapping between different versions of Linux. So it ensures that interoperability between different Linux versions. It's a set of header, a set of mapping that ensure that whatever your Linux version is, your program will work whatever. What would happen is, because if you compile your bytecode in your machine on version 7 of the Linux kernel, and the production is on version 6, some functionalities would be missing, and your program would basically explode. BCC solves that, the program or the Python library I mentioned, by delaying the compilation until the production servers. The problem is you will need to do the compilation every time you run it in whatever your fleet is, the number of servers you have, which is really time consuming. BTF is the community's answer to that. I only have 7 minutes, a demo, and then numbers of slides. So I'm going to run a little bit fast. The second demo is basically a load balancer built using Rust, Docker, PS. So I have 4 containers, backend number 1, backend number 2, a load balancer, and the client. And the client is this one. So what I have is Aya come with predefined structure. People in the back, can you see the code clearly? Cool. It's the common library, which contains different, common things. No, not this one. Oh, it contains common things, have nothing in there. The load or XDP LB, it's the user space. It basically loads the programs and runs it. And I'm cheating a little bit here, and I'm defined a map which contains 2 addresses, which are basically the last bit of the IP address of my containers. So the map key number 0 contains the first backend, key number 1 contains the second backend, and those created within the user space and loaded into eBPF maps. The interesting part is this one. Okay, let me delay that. A lot of code. Here basically loading the libraries, defining the headers. Of course, I'm dealing with the networks headers, so I need Ethernet, I need IP4 headers and TCP headers. I'm defining the address of the client and the load balancer. Probably the numbers are missed here because I needed to upload them, but whatever. And then what I'm doing is loading my program, and if the program executed successfully, return OK, otherwise drop the request, because like something happened. And then I'm starting to receive a request, which is a network packet, making sure that it's an Ethernet header. Otherwise, pass it. I don't want to, I'm not interested in anything that is not Ethernet. Reading IPv4 addresses, if IPv6 pass, reading TCP header, and there where the fun happens. So I'm reading TCP, getting the source IP and the destination IP, and checking the initial checksum, and then randomizing here. So what I'm doing here is basically getting the time in nanoseconds, and then if it's divisible by 2, 1 or 0, and that's similar to here. Remember my map, it was 0 or 1, so if is it the modulo? Whatever. The rest of divided by 2 would be either 0 or 1. So I'm a little bit of cheating here because of how Docker or container works. And what I'm doing is getting the backend address, which could be either 0 or 1 here, getting the full IP, and then mapping it. So I'm changing the source address to my client, which was number 4. If the request is coming from the client, then change the backend to whatever, put the IP address. I'm changing the header and the IPv4. Otherwise, just let it pass, and then changing the request of the source address to load balancer, because like the request comes from the client to the load balancer dispatch it to either backend 1 or backend 2, and what I receive needs to be changed. And then I struggled with this part a lot. I needed to calculate the checksum, which was, oh my god, it was super hard to do. I salute the folks that does this for a living. And that's basically it. What I have here is my program is running. I already run my program, and this is my client, which is this one. So hopefully if I run, I don't remember, I think I run it just before here. Yeah, so 15 is the address. You need to trust me with this one because I'm running out of time. Is the address of the load balancer. And if I run it, so we got 17 in the first one. Hopefully we'll get 16 at some point. Please, please, please. No, please. No 16, please. Yes, okay, yeah. And then hopefully you notice that whenever we run this, there is a request happening in the load balancer. That's basically what it does, and I have the link to the slide in there. I have a lot of slides, but 2 minutes left. Let's see where we can go. eBPF is cool, but should we do basically everything in eBPF? Not really. The TLDR here is everything that is CPU intensive needs to stay within the user space. Nothing that does a lot of calculation, a lot of stuff needs to be moved to the kernel. Here is a cool demo from, or a cool analysis from the Cilium folks. Cilium offers an eBPF4 or XTP layer 4 load balancing, and the graph is inversed. I don't know why they did this, but it's weird. So IPVS is basically their client before moving to eBPF, and that's how much CPU they were using basically, which was a user space load balancing. When they switch it, which is the L4LB, which is L4 load balancing, XDP level, then you see there is almost 200% drop, like from 20% CPU to almost nothing. And that's only because they move it to whatever load balance into the Linux kernel. The tooling, that's the fun part. You would probably never need to write eBPF programs, but more of using the tools that they are there. Brandon Grech, I mentioned this before. They have a lot of tracing tools, really cool, that covers pretty much everything within the Linux kernel. Give it a shot. Katran, that's from Facebook, and it was announced on 2018. And you can assume it was used way before that. So Katran is open source project from Facebook, and basically everything that goes into Facebook network goes through eBPF XDP load balancer. It's open source, and a lot of people are using it. So when Facebook open sourced the project and started talking about eBPF, eBPF just exploded in popularity because in the blog, this one, they mentioned a lot of improvements and saving costs that they have and how it enabled them to run things faster. Um, Cilium is one of the, oh wow. Can I have 1 minute? I'm not sure where I can get. Cilium is one of the contributors at eBPF. They have a lot of tools. They're focusing on networking, but he also offers security as well. In security, a couple of projects that are popping up in the Safe project: Falco, Tetragon, Calico. Really good. Observability, you probably heard about Pixie or Periscope. Periscope is from Grafana. Pixie is a Safe project from the monitoring tool. I forgot what's the name, but it's a very known monitoring tool, cloud. And we have Parka. Pixie is my favorite one. It does more than observability. It also offers tracing and a lot of things. I'm probably skipping this part. It basically says that in the cloud native environment, we have the kernel that is shared between different environments, and there is a growing trend within the cloud native community to use eBPF rather than sidecar proxy. Like SCU are moving to sidecar less. If you heard the sidecar less word in cloud native, especially in service mesh, it means that you are switching to eBPF mostly, taking that functionalities from the sidecar and dumping it into eBPF because it saves a lot of resources. The sidecar was between 2 to 5% overhead, which is a lot in a cloud native environment. And yeah, another graph showing how eBPF is awesome. That's the sidecar that I mentioned, blah, blah, blah. eBPF for Windows, that was fun. I just introduced this as a meme. Windows now is trying to include eBPF in Windows as well. They can't use eBPF as is because like Linux is GPL. They are not, so they need to come up with their own. There's a foundation with a lot of actors, Google, Intel, Cilium, which means and that are investing heavily in the project and boosting the adoption. How eBPF would be probably used in the future? More of kernel development, meaning that we will focus on the kernel, and a lot of the functionalities we'll probably get from eBPF programs that we can easily add as plugins. And then hotfix. When there are zero-day kernel vulnerability, instead of waiting, there is a patch on something, you can write an eBPF program that can basically fix that functionality from the kernel. Thank you, and those are the resources. Sorry for being over time.